Hey, welcome to Ones and Zeros. My name's Ben, and today we're taking a look at another one of our STM32 Basics series of videos. Specifically going to be taking a look at the I2C bus today, or otherwise known as I2C or the Inter-Integrated Circuit Bus.
Hey, welcome to Ones and Zeros.
Basically a bus that is designed to allow communication between different peripherals. And much like SPI or UART or CAN bus, things like that, it's just a way to allow multiple different systems to be able to communicate with each other. So we're going to sort of have a bit of a look at what it is, a little bit of how it works. We've got the oscilloscope set up so we can actually have a look at kind of how the communication actually works with I2C. I typically will pronounce it I2C simply because it's easier, even though technically it's I2C. So we'll have a bit of a look at that. We've also got we pop over to our camera, so we've got our Nucleo 64 board with our STM32 F411 set up, ready to go. And connected up to that, we've got a ADXL, what is that, 345 accelerometer module connected to that. And then we've just got the oscilloscope set up, monitoring the two signals that are used for the I2C bus. And we can see that the oscilloscope's currently sitting there showing us some decoded information that has been transmitted. So we're going to sort of get into a bit of a breakdown of what that is and how it all works and that sort of stuff as well. So what we'll do first up is just kind of describe what it is and how it works. So we'll jump over to this one, and we can essentially think of I2C as being like two wires basically, as all that's needed for communication. Excuse my bad drawing. And then connected up to that, we can have multiple different devices. So say this is our STM32, and that's connected up to our lines like that. And then we can have another device, so say our ADXL. My writing's terrible today, either not enough coffee or too much. And then we can have as many other devices connected up to this as we like. So say any example of the F769 discovery board that we're using with our Discovering STM32 series is actually using the I2C to communicate with both the touchscreen controller as well as the audio codec chip to be able to control that one. And you'll also find that it's used to communicate with multiple devices on the F407 discovery board as well as the F429 discovery boards that we've been looking at code bases for as well. Now, as far as these two lines that we've got, one of them is, that's a really terrible C. Let's just rub that guy out. Let's try that again. So we have our clock line and we have our data line. And our clock line is used to determine the rate or the speed that the communication happens, while the data line obviously is the one that actually carries the individual data. So if we jump back over to this one here, and just pop that guy over there for the moment. So we can see on the oscilloscope screen, we've got our yellow signal and we've got our purple signal. So our yellow signal is our clock line and our purple signal is our data line. And we can actually have the oscilloscope set up so that it's actually doing an I2C decode at the moment. So the list that we can see up near the top of the screen is actually the individual bits of information that are being sent, so the individual packets. And we can actually zoom in and have a bit of a look at those guys. So if we zoom in to this first one here, see if we can get a bit closer there. That looks a bit better. And we'll see if we can get the camera zoomed in a bit closer on that one as well. There we go. All right, so this section here, let's see if we can bring up some cursors. Let's jump over to this one. We'll move that over to about there somewhere. So we can see we've got one cursor set up here, and our other yellow cursor set up here is basically one section of information that's being transmitted. In this case, it's basically sending a write command, and each device on the I2C bus effectively has its own address. So one of the first things that is going to happen is that the device that's transmitting or either sending out a request to read or write from another device is first going to send what's known as a start, which then tells all the other devices to listen on the bus. It's then going to send out an address over the data line, which is aligned with the clock signal, which is our yellow signal there. And the device that matches that particular address is the one that's then going to continue listening. The 8 bits that are sent, or if you're using a 10-bit address, then it may be 11 bits, but we'll stick with 8 for the moment. So the first 7 bits are going to be the address, and then there's going to be that final 8th bit, which will determine whether the transmitting device is wanting to read or write from whichever device it's addressing. So in this case, for this particular packet, it's basically telling our accelerometer here that it wants to write to it, and we can see that it's sending the address, which is this first half of the packet here, followed by just a bunch of zeros. So that kind of gives us a bit of a breakdown of how the communication happens. We can also explain it a little bit better with some of the diagrams that are actually in the data sheet for the accelerometer as well. So if we just pull these guys up, so jump over to not that one, we want this one. All right, so see if we can zoom in a little bit more on that. That's a bit better. All right, so we can see here some of the different types of transmissions that can actually occur. So we can see if we're doing a single byte write, so wanting to write a single byte to a particular register on another device, it will send the start followed by the slave address and acknowledge that it wants to actually write to that. The device that matches that address will then send an acknowledgement to say it's ready to go. Then it will send the address of the register that it actually wants to write data to. Sometimes that can be an 8-bit address, sometimes it can be a 16-bit address, depends on the particular device. And then the receiving device will then do another acknowledgement to say that it's ready to go for that. And then the data will be sent, followed by sometimes, but not always, not acknowledge. Typically, if we're writing, there's going to be an acknowledge here, followed by a stop signal to say that the transmission is finished. A multiple byte write is fairly similar, except between each chunk of data that's being sent, we're going to have an acknowledge followed by the next bit of data so that the master device knows that it can continue to transmit. And then in the case of a read, it works a little bit different because of the fact that we have our start and then we send our address and tell it that we want to write. Then we get our acknowledge, then we write our register address, which is why we're telling it here that we want to write. We write the register address to the slave, which then acknowledges that. We then send another start, and then we do the slave address again, followed by a read signal. And then we get the acknowledge from the slave, and then the slave will then send the data back to the master. And at that point, we won't get any acknowledgement signal, and we'll get our stop. And our multi-byte read kind of works similar, as we can see there, except we have our extra acknowledge from the master. So essentially, if we jump back to our scope and we go to, let's get rid of our cursors for the moment. Our actual start is signified by the fact that we can see our data line goes low prior to our clock line going low. So the natural state for both of those lines when communication is idle is for them both to be a binary 1, or in this case, they'll both be sitting at 3.3 volts. Now, our stop is kind of similar, except what will happen is the clock signal will go high and then the data signal will go high, and that's kind of what our stop is. We can also see on our little list here of the transactions that are occurring, we can also see when an acknowledge has occurred. So if we get one of these in the list with the little tilde symbol and the A after it, as we can see on the second and the fourth line there, that tells us that there's been no acknowledgement there, which in those cases there doesn't actually need to be. So that kind of gives us a bit of an idea of how that works. And then overall we get our communication occurring, as we can see if we zoom back out. So that's actually 7 different transactions that are happening there. So the first one is essentially we are doing a read. So the first transaction is writing the register address from the master to the slave. Then the master is reading the data from that register from the slave. And then it's doing that for another register, followed by doing a write, and then we're doing another read. So that's kind of what that is, but we'll break that down as we get into the code a little bit anyway. So similar to what we've done for a bunch of our other videos previously so far, we are firstly just going to sort of see how to actually get that set up in a bit of a rough way in our code. So let's jump over to that one for the moment. So just looking at the code base from our STM32 basic series, leading on from the last video that we did, which I believe was the real-time clock. And we're just going to be adding to it from there. And this driver that we end up writing will also get ported over to our other code bases as well, so that it can be used across all of those. So essentially, as I mentioned, we're first just going to roughly get it set up like we've kind of done previously, just so you can sort of see how to get that set up with the HAL. And then we're going to go through and actually get a driver written for it that we can then use a little bit more dynamically. And that driver is basically the one thing I've been waiting on prior to doing any more of the Discovering STM32 videos, because we actually need this I2C driver to get the touchscreen set up for that series. So there is also a few other of the communication standards that we're going to be looking at in upcoming videos. So the next one after this, we'll be looking at SPI, or the Serial Peripheral Interface. Following that, we are going to take a bit of a deeper look at UART or USART, which we have looked at already in episodes 3 and 4, I think, of the Discovering STM32 series, but we'll actually have a look at a bit more of a hardware level. We can use the scope to do some decode for both the SPI videos and the UART videos. And we'll also take a bit of a look at CAN bus as well. That one will be coming up. which is much like I2C, is a bus that allows us to easily connect multiple devices using just a couple of wires, which is really cool, but has a bit of extra flexibility to it that I2C doesn't have. And you'll typically find CAN bus used in things like your car and machinery and industrial equipment, things like that, because it's really good for that sort of thing. Other things that we will look at in future will be the SAI interface and the I2S interfaces, which are specifically based around transmission of audio. But we'll also see how we can actually transmit data using those guys too. So all of that stuff will be coming up. So first things first, let's get stuck into some code and we will see what we can get happening here. So just going to scroll down in our main, just after where we've got our message being sent out that our device is booting, and we are going to start getting our I2C or I2C set up. Might need a little bit more coffee prior to doing that, however. So definitely much better. All right, and let me just get that fixed up so that that's good to go shortly as well. Wonderful. All right, so much like we've done previously, the first things we're going to need to do is get the GPIOs set up that we're actually going to be using for this communication. So in this case, we're just going to need 2 pins, one to act as our clock pin and one to act as our data pin. So of course, the first thing that we're going to need there will be a GPIO init type def, which much like we usually do, we'll just call GPIO init and we'll fill that guy with zeros. And we'll do our clock pin or SCL pin first. And at the moment, we've got this guy connected up to, is it pin number 10 on this device? And you will find the specific pinouts for this. So this device has 3 separate I2C peripherals, I2C 1, 2, and 3. In this case, we're going to be using I2C2, and you will find in the datasheet for the particular STM32 device that you're using which pins can be used for the clock and data lines for that specific device. So if you run into any questions with that, feel free to leave a comment or jump on our subreddit or send an email and we'll see what we can do to help out with that. Now, our mode for this one, we've used our alternate function push-pull mode, this guy, for a couple of our different peripherals so far. In this case, with I2C, both of the GPIOs are going to be using open drain mode, simply because they use pull-up resistors to keep the signals at a digital 1 or our 3.3 volt level. And the device that is actually sending either a clock or data signal is actually then pulling the line down. So it uses the open drain mode. So it's like pulling a plug out of a bathtub and it drains the power out, which then pulls the signal line down to 0 and then puts the plug back in, the charge comes back up and we get back to a binary 1. So all of the devices will use an open drain mode for both the clock and data lines. So we are going to use our pull-up resistor on both of these. Now, the particular module that we're using here, the accelerometer module, does also have pull-up resistors. So we don't necessarily need to use them here, but generally when using I2C or I2C, if there's no dedicated pull-up resistors or even if there is, typically would normally be using the pull-up resistors for setting up the GPIOs anyway. Now, as far as our speed, we don't necessarily need to have the speed turned all the way up as far as our output. We will, in this case, set it to high anyway. We might even chuck it on very high, simply because even in high speed mode with I2C, you're typically looking at a clock signal that's not going to get above 400 kilohertz, so 400,000 cycles per second. In the case of what we were looking at on the oscilloscope before, that was actually a 1000 kilohertz signal, which is basically the typical low speed limit for I2C. Although you can run the devices at even a slower speed than that and it will still work depending on the particular devices that you're communicating with. But the STM32 devices tend to be fairly flexible with the speeds that they're able to operate at, up to the ceiling of 400,000 hertz or 400 kilohertz for the high speed mode. Now our alternate function for this one is going to be GPIO AF4 I2C2, and we'll set up our data pin as well. We might actually want to initialize this one, might help. So that is GPIO B. We'll pass a pointer to our GPIO init structure. And then we'll go through and set up our SDA pin as well. So in this case, we're going to use pin 3. This one is actually using AF9, and that's on port B as well. Okay, cool. So that's our GPIOs done. We need to enable our I2C clock, and for that one we are just going to do a bit of our copy and paste. So essentially just enabling our clock, then we're forcing a reset and releasing a reset on that one. And then we'll initialize our I2C peripheral. For that guy, we are going to need a I2C handle type def, which is what we use for the HAL to be able to communicate with the device. Now, for that one, we are going to want make sure that I get the right one there. Okay, which will be I2C handle type def, and let's call that I2C handle, and again we'll fill that guy with zeros. Now we need to tell it what instance we're going to be using for that one. In this case, it's just going to be I2C2. Might help if I spell that correctly. And then we're going to go through and get some of our bits of information set up that we're going to need in order to be able to initialize the peripheral. So first things first, we are going to tell it what clock speed we're going to be operating at. And let's see if we can get this lined up. So we're going to go with 100,000 or 100 kilohertz for this one. So the same speed as what we were seeing on the oscilloscope before. This particular accelerometer does do the high speed mode, so we could go up to 400,000, but 100,000 makes it a little bit cleaner and neater to be able to view on the oscilloscope. You might notice some of the curved edges and stuff when we zoom into the data on the scope, and that's due to the clock speed. but doesn't really impact the data too much. But you will notice more of that sort of stuff happening at higher clock rates. So if we slowed it down more to say 10 kilohertz, we'd actually get much squarer looking edges on our signals. So for our duty cycle, we're not going to go into too much about what that's used for, mostly because in most cases we're going to be using a duty cycle of 2. So for that one, let me just grab the bit that I want from there. Just make sure I get it in there correctly first time. So I2C duty cycle 2. There is also an option for a duty cycle of 16_9, which can be used by some devices. We need to do what addressing mode we're going to be using. So as mentioned before, typically most devices are going to use 7-bit addressing. Some devices use 10-bit addressing. So in this case, we're just going to tell it that we are going to be using our 7-bit addressing. Like so. There is an option for dual addressing mode, which is used when the STM32 is acting as a slave device, but we're basically just going to keep things simple for this video and use the STM32 as a master device and treat the accelerometer as a slave device, just so that we can kind of see how that communication works. We will come back at a later stage and have a look at a bit more in-depth of some of the more complex approaches that you can have to I2C, but we'll keep it fairly simple for this one. So this will be addressing, no, we've done addressing mode, we want dual. It's quite humid here today. It's been raining most of the day, so I apologize if I get a little bit sweaty. So dual address, disable. I2C handle init. General call mode, which we're not going to get into too much in this video, again just for keeping things simple, but essentially we are disabling this one. And there is also a thing known as clock stretching, which can be used for some I2C communication. In this case, we're also going to be disabling that one as well. And good to see I'm losing my voice already. So no stretch, disable. And then, excuse me, for instances where the STM32 is being used as a slave device, we can also set addresses for it. So, and we can set 2 addresses for it if we're using dual addressing. In this case, we're just going to set both of those addresses to 0s. And that's basically all we need to do to fill out our initialization structure there. So we can then go through and call HAL I2C init. We'll pass it a pointer to the handle, and we'll check to make sure that that has actually been successful. And if it hasn't, then we will turn on our user LED. We will also send out a message via our ST-Link UART. And we'll just say I2C initialization failed. And we'll also jump into an infinite while loop, similar to the approach that we normally take. So we will If it's successful, send out a message just saying that it's initialized. Now, the other thing that we're going to need to do is to also enable that peripheral as well. So for that one, we are just going to use HAL I2C enable, pass it a copy to the handle, and I'm using the wrong name there, so let's fix that up. Like so. So basically at that point we are ready to go through and actually start doing some communication. Now what we're going to do is basically most I2C devices will come with a chip ID register, and I typically find that when I'm going through and actually getting all the devices on the I2C bus initialized, the thing that I like to do first up is read from that chip ID register from each of the devices that I'm wanting to access, making sure that I'm getting the correct ID from each of them, so that I know that that communication with that particular device is working correctly. So basically, that's what we're going to look at doing first up. So we are going to use let me just grab this one and we will copy and paste that. Going to use this particular guy here. For our timeout, we're just going to put in 1000 for that one. For our length, I believe that should just be 1. We're going to need something to store our data into as well. So that should actually provide us with the actually no, I'm doing that incorrectly. So we still need to create our variable to hold that, but we are going to pop that in here. Actually no, that should be that one. This will be our actual register address, which will be 00 for this particular register. Let me just double check that I'm getting all of these bits right. Okay, no, not getting that right. So our register address will go there. This will actually be, no, we don't want to help. This one here will be a 1. This will be our actual device address, which we'll have a look at in a second, and this will be our handle. So we'll grab our device address. So if we jump back into our documentation here, in the particular bit for our I2C communication, so this ADXL345 can actually be used in I2C or SPI mode. In this case, we are looking at the alternate address, so 0x53 will be the address that it's going to respond to. So if we jump back to here, That's the address that we're going to pop in there. Just double check I've got that right. 53, that's correct. But we're also going to have to shift that one bit to the left so that it is left aligned, because the rightmost bit is our read or write bit. So we'll just going over that again. Basically, our first thing that we pass to this one is our peripheral handle, then the address of our device, which again, we're shifting one bit to the left. So the actual read or write bit is taken care of by the particular HAL method. So if we were using HAL I2C mem write rather than HAL I2C mem read, then it's going to take care of the read and write bit specifically depending on what we're asking it to do. We're then passing the register address that we're actually looking at reading from there. So if we jump up to, where are we? That is in our register map section of this document. So we can see the register that we're looking at reading is our device ID register, which is located at address 0. So, and this here is the value that we're going to be expecting to get back from the device if it reads successfully. So hopefully that kind of makes sense. So passing it register address 0, telling it that the register address is 1 byte in length. We're giving it a pointer to where we want it to store the data that it's reading, which is the variable that we've created there. We might even initialize that as 0 just so that we know that, if make it a bit easier for us to see whether or not we are actually getting the correct data. This value here is telling it the length of the data that we actually looking at reading. So in this case, just 1 byte. And then the timeout value is used to determine, so if the master device, so the STM32 in this case, doesn't receive the acknowledge in a certain period of time, then it's going to cancel the transaction and will then return an error. So we will also check to see if this one succeeds or not. And if it doesn't, then we will just send out a message saying that that has failed, and we'll jump into an infinite loop. However, if it succeeded, then we want to know what the value is. So let's create a string to pop that into, and we'll use sprintf to format that for us. And let's print that out in hex. So we're going to go 0 to x for that one. And then we will use our udata there as our value. And then we will print that out via our ST-link serial like so. All right, so hopefully that'll make sense. So we've initialized our clock and our data GPIOs, enabled the clocks for our peripheral. We've set up our peripheral itself, enabled that peripheral. All of this sort of stuff's probably getting fairly familiar by now, because for most of the peripherals in the HAL, it's going to be fairly similar. And then we're basically asking the HAL to get the I2C peripheral to read the ID register of our accelerometer and see what value we get back. And assuming that succeeds, then we're just going to print that out. So let's first just check and see if we've managed to score ourselves any bugs. 3 errors. Where are they hiding? Ah, okay. Can't spell LED correctly. 0 errors, 0 warnings. So let's pull up our serial. We'll connect that one to our device and we'll go ahead and get our software sent across to the STM32. And we can see that it has successfully done a read and we've got a value of E5. Now, if we jump into our Windows calculator and we've got that in programmer mode, we'll jump into hex, we'll pop in E5. We can see the binary value that that translates into. If we jump into our data sheet for our device and then we pull up our calculator again and we compare these guys, we can see we've got 3 ones, 2 zeros, a 1, a 0, and a 1, which means that we have successfully read the value from our device ID register. So that is the simple approach to getting I2C up. And if you want to take a look at that transaction occurring on our camera, jump over to that one. Let's get zoomed in on that guy there. And we can see the 2 transactions that have actually taken place here. So the first one is where it's done the write and it's written a value of 00 to the correct address for this device to say that it wants to read from register 00. And then it's done the read transaction and we can see that it's pulled back the value E5. With no acknowledgement at the end of that because we're doing a read. So that's kind of how that basically works. We might just get the camera zoomed in on that one a bit so that you can get a bit of a better shot of that, like so. So as we can see, the 2 transactions showing up there on the list and the particular values. Even though the device address is 57, you're going to see the A6 and the A7 because don't forget the device address is shifted across to the left by 1 bit, and then you will have the extra bit set for the read, which is why it's A7 rather than A6, because that 8th bit is set to tell it that it's doing a read, whereas it's not set when we're doing the write. So hopefully that makes a bit of sense. So what we're going to look at doing next is going through and getting a bit of a dynamic driver written so that we can go through and have a look at some of the more dynamic approach that we're going to be using and the particular driver that we'll be porting across to our other code bases moving forward as well. Prior to that, however, I am just going to take a quick bio break because we are about 50 minutes in. And I will be back in a couple of minutes and we'll get us a driver sorted. So see you in a moment. And we are back. So thanks for waiting. Just grab some coffee. And let's get us a driver written. So first things first, we're just going to comment out all of what we've done for this bit of the example, and I will leave that in there. Again, this code will be going up onto GitHub not long after the end of this stream, so if you want to check out how we've kind of set that up there, that'll still be in there, just comment it out. And I do believe that you can actually roll back to previous iterations of the code in GitHub as well to see the various versions. If there's a particular thing that we've removed that was done in a previous stream that you want to check out. If you've got any questions about that, again, feel free to leave a comment or jump on a subreddit or send us an email. Addresses for all that stuff's down there. So yeah, let's get on with the driver. So much like we've done with our timers and our UARTs, we're actually going to be setting up a peripheral manager for this one because we have our 3 different I2C peripherals, and we want to make sure that we're not trying to set up 2 different driver classes that are both trying to use the same peripheral at the same time. So if we jump over to the screen, we can see, just ignore the GPIO ones for the moment. That's something I'm kind of experimenting with moving forward, but we've got our timer manager and we've got our UART manager. So we're also going to be creating one for our I2C. Might help if we spell that correctly. So I2C manager.hpp. And we also want a new source file, which will be QAD I2C manager CPP, and we don't want a template for that one. Now we're also going to need a couple of files in our actual drivers folder, which will contain the actual driver class itself. So we're just going to go with QAD I2C.hpp and QAD I2C.cpp, like so. Now let's pull up this one just so that we can copy the header from it. And I'm not going to worry about doing too much of the commenting of this in the stream as I've done previously. The code will become a bit more heavily commented moving forward, and that's something that I don't want to bore you guys with too much. So go through and fix up our prevent recursive inclusions. I2C manager HPP. Now, what are we, the 25th today at the moment? And this will be I2C manager. And this will be our I2C management driver. We want to include setup.hpp in that one, so let's save that. We'll grab all of that and we'll copy that over to our I2C manager CPP file. Change the name of that one to CPP. Remove our prevent recursive inclusions, and we'll be wanting to include our QAD I2C manager.hpp file in that one. I'll also dump this over into our I2C HPP file. So this will be for the actual driver class itself. Fix up our bits there and get rid of the manager part there because it'll just be I2C.hpp. Grab hold of all of that again, and we're going to copy that over to this one. Change him to CPP, get rid of our prevent recursive inclusions, and and this one will be wanting to include QAD I2C.hpp. Now, our I2C.hpp file will also want to include the I2C manager. So we'll put in I2C manager.hpp in there as well. And that's basically those 4 files roughed out and ready to go. Now we're going to do a bit of copy and paste again, just to make things a little less boring for you guys watching, but I will explain sort of what we're copying and pasting as we go. So first things first, we are going to want these guys here. So first one is an enum to select which of the 3 I2C peripherals that we want to be referencing. So I2C 1, 2, and 3. We're also, as you'll have noticed in some of the other managers, we're including an I2C none there as well, which is used as a return value for a couple of the manager methods, but it's also used to allow us to more easily grab a count of how many peripherals, I2C peripherals, are available on this device. So part of the reason why I do that is so that when I go to port this driver over to another device, say if it's got 4 or 5 I2C peripherals, then I can just add those extra guys to this enum here, which will then increase the value of I2C none. So if we hover over that at the moment, we can see it currently equals 3, which tells us that we've got 3 peripherals. So it just makes things a little bit easier. And then we've got some different states that we've got set up here. We're only going to be using the master state in this particular video. We're going to have a look at the slave and multi modes that we'll set up for the driver in future videos, where we start to do a little bit more advanced stuff with I2C. We're also going to want a structure that we can create an array of within the driver manager to hold the current states of the 3 I2C peripherals. And inside there, we want to be able to know what the enum is for that particular peripheral, so we can retrieve that, what current state it's in, which is our state enum. We also want to be able to grab a handle to its instance, which is then used when we go to set that up. So similar to what we've done when we've told it our instance in here. And then we've also got our 2 different IRQs that are available for that particular I2C peripheral. So each of the I2C peripherals have an event IRQ, which is typically going to be called when something like a read or a write has finished occurring, if those particular interrupts are turned on. And then you've also got a separate error interrupt that can be called as well if there's actually an error with the peripheral, say if a read or a write has timed out or something like that. So not going to be using those too much in this video either, but again, just sort of setting those up to future-proof. And then we've got the actual manager class itself, which we are also going to copy and paste in. Fix up our indents. And again, this manager class is being set up as a singleton method because we only want one manager to be able to exist. So if we have a look at the class, we've basically got an array of our data structures here to store the data for the 3 specific peripherals. We've got our constructor for the class, which will be defined in our CPP file. That one's made private because that will actually get called the first time our get method is called. Again, I'd recommend maybe having a look at some of our previous videos if you're a little bit confused about singleton classes. We will also have one of our C++ videos coming out shortly, hopefully in the next week or two, where we will actually be specifically looking at normal classes as well as singleton classes and explaining those guys a bit better. But basically a singleton class is a class where only one copy of it can ever exist. So we don't want to be able to have two I2C managers, for example. And as a result of that being a singleton class, we also want to go through and delete our copy constructor as well as our assignment operator so that we can't create multiple copies of that class. We also have all of our static methods, which are the methods that are going to get called from outside of the class because it is a singleton class. So we'll have a look at sort of how we use that, but you may recognize that from previous videos as well. And then we've got all of our implementation methods, which will be defined in our CPP file as well, which we'll go through and have a bit of a look at. But basically, we've got methods to be able to get what the current state of the device is, so whether it's being used or not, and what mode it's being used in if it is being used. We've got a method to be able to retrieve the instance for a specific peripheral so that we can go through and get it set up within the driver. We've got methods to be able to retrieve both the event and error IRQs so that we can go through and get the IRQ set up within the driver if we want to be able to use those. We've got a register method and a deregister method. So if we register the peripheral, we're basically telling the manager that we're actually using that. So the register method will then go through and check that the peripheral is not already being used. If it's not being used by anything at the moment, then it will go through and actually register it as now being in use and what mode it's currently being used within. And then once we're finished working with that peripheral, then we go through and we deregister it so that another driver can come along and use that peripheral if it wants to. We've also got methods to be able to enable and disable the clock for the particular peripheral, so the same as what we've done here. And finally, we've got some methods just so that we can actually check how many I2C peripherals are currently in use, as well as a method to check how many I2C peripherals are currently not being used. So again, once we start to look more at turning the Quartz-Arc codebase into a bit of a microcontroller operating system, those are methods that we're going to be using to be able to monitor what peripherals are being used and things like that a little bit easier. So that stuff will be coming up after we've had a little bit more of a look at some of the basic stuff. So let's get our method declarations or definitions, copied over from here into our manager CPP file. So we've got the definition for our constructor, which is basically just going through and filling out the data for each of the three peripherals in our array that we've got set up. So in this guy here, so it's just making sure that when that manager class gets created, that everything's set up correctly for each of the three peripherals. And then we've got the various definitions for our method to register and deregister the peripherals. The methods to be able to enable the clock for a specific peripheral or disable the clock for a specific peripheral, as well as the ones to be able to check how many peripherals are being used and how many peripherals aren't being used. So that's a bit of an overview of the manager itself. And then let's move over to our actual driver class. So with this one, we're first going to define a bunch of enums. And you'll notice that we've defined enums for a lot of the things that we used when we were setting up the peripheral in main CPP earlier, so where we're using, say, our I2C addressing mode 7-bit, we've actually got an enum set up for that. And the reason why we're using enums for these to reference the actual items from the HAL is because it then gets the compiler to double check that we are using the correct type of value for each bit of information when we go to set up a peripheral. So it gives us that extra little bit of protection without us having to worry too much about whether we're passing the correct value. The compiler is going to double check our work for us on that one. We're also going to have an initialization structure, so similar to what we've done for most of our previous peripherals, where we basically go through and fill out the details for how we actually want that peripheral set up. So, for example, our details for our clock and our data GPIOs, as well as our IRQ priorities, which peripheral we want to use, whether it's I2C 1, 2, or 3, as well as the details of how we actually want the peripheral set up, so clock speed, duty cycle, addressing mode, all of that sort of stuff as well. So we fill that out, and then that gets passed to the constructor for the class itself, which we will grab from here. And feel free to leave a comment if you feel that I'm going through this stuff too quickly or not quickly enough or things like that. That feedback does come in handy. I do want to try and make it so that it's interesting, but also make it so that it's not going to bore people senseless as well, which is why we're doing a lot of sort of copy and paste and stuff to get all of this stuff moved across rather than you sitting there and watching me type it all out. So we've got our QAD I2C class, which is our actual driver class for a specific peripheral. You'll recognize things like our deinitialization mode. So that one's used in a case where we go to initialize a peripheral and it fails partway through and we just need to partially deinitialize it. Or if we need to fully deinitialize it in the case where it has been completely set up and we no longer want to use it. We've got different bits of information that we're storing here. So our timeout constant, which if we go back to where we did the read of our ID register, we typed in a value of 1000 there. So we've just got a constant set up inside this class which stores our particular timeout value. A couple of constants here, to say how many bytes are included for an 8-bit memory address, which is 1 byte, and 2 bytes for a 16-bit memory address. We're storing an enum for whether or not the driver is currently initialized or not. And that one is defined over in setup.hpp. So that's our QA init state enum. And we've also got our active state enum, which defines whether or not that driver is currently active and able to be used. Again, similar to the approach that we've taken with all of the other drivers that we've done so far. Let's fix that indent up as well. We're then going through and just storing a bunch of the information from our initialization structure so that that can be stored within the driver, as well as our 2 IRQs, so our event and our error interrupt, and the handle that we use when using the HAL methods to be able to manipulate the I2C peripheral, as we did when we created that handle in main just there. So that's all of that stuff there. We've got our default constructor is being deleted because we do need to hand a copy of an initialization structure to the driver in order for it to be able to be set up. So we don't want our default constructor being used, so we delete that one. and we then go through and set up this constructor, which we can hand a reference to a QAD I2C init struct, and then go through and fill out a bunch of the details that are stored in the driver up there, so that all of that stuff is ready to go for us to then initialize the driver. We've got our destructor, which will go through and firstly check to see if the peripheral is active, and if it is, then it will go through and stop the peripheral, and then it will also check to see if the peripheral is initialized, because if it is, then it wants to go through and deinitialize that, deregister it from the I2C manager and things like that, in order to make sure that everything is done gracefully. So if we create the driver, we use it, and then we destroy it again, everything's back in the same state it was in prior to us creating the driver. Again, making sure that when we start to do things a bit more dynamically moving forward, that we're not going to run into any sort of issues as a result of drivers being dynamically assigned to various things. We've then got our init and deinit methods, which are used to initialize and deinitialize the driver. We've got a method to return what the current initialization state of the driver is, so whether it's initialized or not. And we've got one to be able to retrieve a reference to the handle type def that's being used, just in case we need to be using that one in future. We've got some control methods to be able to start and stop the driver, and also to be able to check whether it has started or not and whether it's currently active. And we've also got some methods to make it a little bit easier to be able to do different types of reads and writes to various peripherals. So for example, we can do an 8-bit write or a 16-bit write, or if we want to write multiple bits of data, we can use that one. And same again for our reads with our 8-bit, 16-bit and multiple 8-bit. And then we've also got our private methods, which are our perif init and perif deinit methods, which is where we actually do most of the initialization and deinitialization stuff. And then we've also got a couple of tool methods which are used by these write and read methods. Basically, we'll call these ones, and it kind of helps simplify the read and write process, given that if we go back to when we did our test in here, and we've got a whole bunch of different bits of information that have got to be handed to our HAL method in order to do a read or write. Basically, these tool methods just help simplify that down a little bit, so that we don't have to pass things like the driver handle and things like that. And again, we can see that when we get to actually using these methods, which are the ones that we're calling, we're only going to be handing 3 or 4 bits of data, 3 or 4 parameters to each of those functions or methods when we go to call them, rather than, I think it was 6 that we had to pass, or 7. Can I count? Was that 7 different parameters that we had to have to hand to that I2C memread method? So to keep things simple, we don't want to have to pass a bunch of redundant information. That just helps simplify all of that a little bit. So that's kind of why we're laying it all out that way. So let's get our actual methods definitions copied across as well. So again, good old copy and paste. And all of this is the code that we were using when we were first looking at the very start of this video at what was on the oscilloscope. All of that was running using these drivers. So we're going to go through and have a look at kind of how we went through and set that up, and what we're actually doing as far as reading and writing and things like that. So we've got the definition for our init and deinit method. So basically our init method will first go through to check whether the peripheral is available or not. If it is not currently being used, it will register it, and then it will go through it and attempt to initialize it. If the initialization fails, it'll then deregister it so that the manager knows that, okay, wasn't able to initialize it, so it's currently not being used. And then it will return a value to let us know whether the initialization was successful or not. Similar for our dinit, it's firstly going to check to make sure we are actually initialized, because if we're not, there's no point trying to deinitialize. It will then go through and deinitialize the peripheral and then tell the I2C manager that we're no longer using that peripheral so that the manager's aware of that. Our get init state basically just returns the me init state value that's stored in our class, and similar with our get handle, basically just returns the peripheral handle there. Our start and stop methods basically just enable and disable the peripheral respectively, as well as keeping track of whether it's active or not in our me state variable. So similar to how we used our HAL I2C enable function there to be able to basically turn the peripheral on after we had it set up. That's basically what these guys are being used to do, and then this method here is being used to check what state that's currently in, so whether it's active or not. We've then got our various methods to write various types of values that we talked about before, as well as the ones to read those various types of values, so 8-bit, 16-bit, or multiple for those respectively. And then we've got our main, so our private methods, so our main initialization method, which is doing basically the same thing we did over here, where we initialized our GPIOs, turned our clock on, and got the peripheral set up. So we can see all of that same sort of stuff going on here. So initializing GPIOs, telling the peripheral manager to enable the clock, initializing the peripheral. This also does go through and set up the event and error interrupts as well, which is again something we're going to use in future. And then also sets the driver state so that we then know within that driver that it is initialized but it's currently not active. And then our deinitialization method basically goes through and does the reverse of that. If the driver is currently active, it's first going to stop it. So disable the peripheral, disable the IRQs, deinitialize the peripheral itself, tell the manager to disable the clock, deinitialize the GPIOs, and then let the driver know that the peripheral is not only inactive, but it's no longer initialized as well. So that's basically what those are doing. And then we've got our tool methods to be able to do our writes and reads, which I kind of explained a little bit before, so won't go over that too much again. So now that we've had a look at those guys, let's actually have a look at making use of it. So let's include QAD I2C.hpp in here. We're going to create a I2C test driver, and we're going to call that QAD I2C, and we'll just call that I2C test, and that should actually be a pointer to a QAD I2C class there. So we'll go down to just after where we were doing all of our I2C stuff before, so just before our processing loop. And again, just going to make use of a little bit of copy and paste for this one, and then I'll go through and kind of explain what we're actually doing as we go. So just popping that stuff in there. So basically getting a copy of our initialization structure, so the one that we defined in I2C.hpp. We're then going through and filling it out with the respective details, again using basically all the same settings that we used when we set it up before, same GPIOs, all of the same peripheral settings, so a duty cycle of 2, 7-bit addressing, disabling dual addressing mode, general call mode, and disabling no stretch. and setting our clock speed to 100 kilohertz. We're then going through and creating a copy of that class and passing the reference to the initialization structure to it, so it's got all of that information. We're then going through and initializing that driver class. If it fails, then we'll print out a message to serial, turn on our user LED, and jump into an infinite loop. If it succeeds with the initialization, then we'll go ahead and we'll start that driver, and we'll print out a message to let us know that we've both initialized that and started the peripheral successfully. And then we will go through and we will do the same as what we did before, and we'll read our ID register. Now, I'm actually just going to rename this one from test to ADXL345 so that it matches the code that I've copied and pasted in. Because if we notice here, that's what we've actually called that driver class there, so that we know that that's actually for that specific device. So basically this bit here that we've just copied in is just going to do an 8-bit read, again providing the device address of 53, shifting that to the left by 1 bit, giving it register address 0 because we want to read the device ID register, and passing it a pointer to the value where we want it to put that data. Once we retrieve that, we're basically just going to print that out, and we should see the ID coming out the same as we did before, and then printing that out via serial. So again, let's just check how many bugs we've managed to create in there. And looks like my camera is being a little bit weird again, so let's just jump over to that one. 0 errors, 0 warnings. Alright, so if we pull up our serial monitor, we should see something fairly similar to what we got in these 3 lines here. So let's dump that code onto our device. We will pull up our serial monitor again. And we can see these 3 lines here. So it's booted, and it's initialized and started the driver, and we've got that same E5 value as we got from the previous code. So we know that the driver is actually working correctly. And if we jump over to our scope, we can see that our scope is showing the same data that we were looking at before. So we can see that we've written the register address of 00, and then we've read back the value of E5 correctly from there, which is the correct value that we need to be getting. So we can see there that the driver is actually working. We can also go through and do some additional sort of reads and writes as well, just to make sure that things are definitely working for other various register addresses as well. So if we jump back to that one, and again, here's some we prepared earlier. Copy those in there. So basically what this is going to do is it's going to write the value 00 to register at address hex 31. And then it's going to read that back to make sure that we get 00 back, to make sure that the write was successful. And then we're going to write the value 04 hex to that same register, and then read that back to make sure that we're also getting that correct 04 hex value back. So if we have a look at our data sheet, we'll see we're actually going to be manipulating the data format control register. So that one was just one of the ones that I picked because it's not actually doing too much to the device other than telling it what sort of data format we want to be able to retrieve data in. So we're not actually going to go through and actually look at getting accelerometer data from this device in this video. we'll do a separate video where we look at just that device specifically for that, where we'll be using this same driver that we've done in this video. But basically just going to be doing some test writes and reads to that particular register just to make sure that that is actually working the way we expect it to. So again, we'll go through and build that, make sure that we've got no bugs, and zoom out a bit on the scope because we're going to have a bit more data showing up this time around. So let's actually switch over to that one there so we can see the data that we previously read from our ID register from just before. And then when I go and I dump the new code onto it, we will see that update. So just connecting and writing data now, and we can see the various transactions happening. So we can see, if we might actually just zoom this guy in a bit again. Just so we can see that a bit better. All right, so we can see that we have the first and second line are reading the value E5 from our ID register. The third line is writing 0 to register at address 31. The lines 4 and 5 are reading back the value 0 from register address 31. Then line 6 is writing the value 04 to that one. And then if we jump over to our list, we should be able to scroll down and see right there where lines 7 and 8 is where we've actually read back the value 04 from that register as well. And if we jump back over to our serial monitor, we can see that we successfully wrote and read back the value 0 and then the value 04 from those registers as well. So we can see that the driver is actually working correctly. So that was a bit of a look into I2C or I2C, or the integrated circuit bus, and how to sort of work with it using the HAL, as well as getting a driver set up so that we can use that one. Again, this code will be going up on GitHub not long after the end of this stream, typically within about 5 to 10 minutes of the end of the stream. The code is free for non-commercial use, so there is the licensing details are in the README file on GitHub. If you do want to use this code for commercial use, you will need to get in touch with us in order to discuss arrangements for that. So if we jump over to this camera, we can see the email address down there, the onesandzeros.contact@gmail.com. Get in touch with us on that one if you do want to look at commercial use. If you've got any questions or anything like that, any feedback, feel free to leave comments on YouTube. Feel free to jump onto our subreddit. So getting used to this whole pointing thing. So r/onesandzeros right there. And definitely happy for any feedback or questions, anything like that there, or also on the Gmail address. If you do like the sort of content that we've been putting out, we'd definitely love it if you liked and subscribed on YouTube. As of when I last checked a couple of hours ago, we're now up to 95 subscribers on YouTube, which is absolutely amazing in just over 2 months, I think. And there has been about 1,200 views of the videos so far. So I am super thankful to absolutely every one of you that has subscribed and left comments and has been watching the videos. It does mean a lot that people are actually enjoying the stuff that I've been putting out. So thank you so much for that. And we will have a bit of a devlog coming out in the next couple of days, which will be describing some of the videos that will be upcoming, as well as some of the updates behind the scenes and things like that as well. So keep an eye out for that one. We'll also have some more videos coming out, not just for our STM32 basic series, but also for our Unearthing C++ series and our Discovering STM32 series coming out soon. And we will finally be getting around to doing the first in our FPGA video series soon as well as the first video of a series looking at debugging techniques and approaches and things like that for STM32 devices. So a few things there, but keep an eye out for the dev vlog because we will go into some more detail there. So again, thank you so much for watching and putting up with all of that craziness. Hope you found that interesting and hope to see you next time. Thanks so much for watching.